All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Let's jump into it. I have some announcements, but I suppose I want you guys to be able to read them. So as a lot of you are having trouble with the projects, I've decided to actually give you guys an extension on it. I know several groups have decided to kind of switch from Python to Excel, which is perfectly fine. But since you're actually switching programs, it'll probably take you some time to brush up on that. So I've decided to give you guys an extension, and that will cause somewhat of a ripple effect. So I just want to make sure that you have these new dates in mind. So the extension, I was going to make it a week, but I decided to give you a week and the weekend since it would be due on a Friday. So I just decided to just make it due the following class. And so the projects, the written portion, I've decided is now due on May 4th, which is the Tuesday after, it's on a Tuesday. So that's a week and change beyond when it would have been due originally, which I would hope is enough time for you guys to get things in order. And I would recommend that you pretend it's a week extension and try to get it done by that Friday or Saturday. That way you can actually have your presentations like polished and ready to go by Wednesday, which is when the presentations are now going to be due. And having the written portion done will actually help you get the presentation ready, I want to say, because you are going to be talking about some of the things that you wrote about. So you might as well have a finished product so you know exactly what the end goal was, how you actually did everything, etc. So project is due on May 4th, presentations on May 5th. May 5th was the day that we were originally supposed to have our second test. So what I'm going to do then instead is kind of make the test a take home. We were going to have it during class, but what I will do is I will instead give access to the test for a 24-hour period, in which case you can log in, and during that period, you'll have a set time window to actually upload your work. So on Wednesday at 10:30 a.m., which is when class ends, right? So your class ends around 10:20. So at the end of class, the window will be open, and you will have until 10:30 a.m. the following day, which is Thursday. So you'll have all of Wednesday night, and most of Thursday morning to finish the test. And you log into Gradescope, and within that, whenever you log in, 2 hours from that period is when you have to upload the work, which is a lot longer than you would have had had I given you the test in class. So at this point, I just made the window extra long because at this point, I wouldn't want anyone submitting work late. So if I had given it in class, I would have probably given you around an hour and 5 minutes total to give you enough time to upload and stuff, but give you like 55 extra minutes. That's a lot. Yeah, make sure you get it in on time. And that's sort of it. That's what I wanted to start with.
Wait, Professor, I have a quick question.
Yes.
So is the final still Wednesday the 12th?
Oh, the final date, I don't have control over that at all. So yeah, the final is not going to change. Okay. The dates that I have control of is what we do in class. The final exam date is decided by Fordham. So I can't change that. Yeah. Okay. So today I want to do, I don't know how many I'll get through, but I want to do a bunch of examples with you guys. Let me just remind you of what we did last time. Last time we did this example, we did it using tree diagrams and tables, and we pretty much derived a formula that will allow us to do it formulaically in one shot. And we started by developing this formula, which we call Bayes Theorem version 1. And using that, we developed this formula, which is called Bayes Theorem version 2. Usually when people think of Bayes Theorem or Bayes rule as it is called, this is the formula that they're thinking about. One thing you'll notice is that it is about a conditional probability, but it is used when you know the conditional probability in the opposite order. So if you're asked for the probability of A given B, and what you actually know about is the probability of B given A, you can actually use this formula to help you out sometimes. It has a lot of uses beyond that, and maybe I'll talk a little bit about that today. But yeah, that's Bayes rule or Bayes theorem. And we used that and we got the same answer in a very short period of time compared to, these guys, which again, these guys are perfectly valid methods for doing it, but it's good to know several ways to do the same problem. And then I left this one for you guys to do. This one is in fact something that you'd use Bayes' rule for, as we will see. And we're going to do that first. And then I want to try some problems from over here. I don't know how many I'll do. I'll probably do everything except problem 5, maybe. But we'll see. So that is where we are now. Boom, let's go. All right, so this is the problem. Let's actually do it. Okay, there's a rare and deadly disease. 1 in 10,000 people in the population have this disease. So let's pretend that there's a disease and it's rare. Like, this is not rare by disease standards, but for the purposes of this problem, 1 in 10,000 people have this disease, right? Now, you're a hypochondriac. You believe you have this disease for whatever reason, and you go to get tested, right? Now, when you go to get tested, the test results comes back positive. Now, you're freaking out. Like, you're like, I knew it. I knew this was going to happen, right? So you're totally freaking out at this point, right? So now the doctor is like trying to calm you down. The doctor says, well, don't worry. It's possible it's a false positive. Test isn't perfect. It actually gives a false positive in 1% of cases. It'll only be, test does give a false positive in 1% of cases, but there's a 99% chance that if you have the disease, the test will pick it up. So, all right, there's a 1% chance that it was a false positive. There's a 99% chance that if you actually had the disease, the test would catch it. So the doctor says that to you, there's a 99% chance that if you have the disease, the test is going to get it right. So now you are totally freaking out. There's a 99% chance that I have this disease. And you go home, you try to get your affairs in order, you get your will, you start telling all your children that you love them, your parents, you love them, all this, you're right, you're prepared to go because like, man, there's a 99% chance. Now the question is there actually a 99% chance? Part A of this problem says, what are the chances that you have the disease given that this just happened? And that's what we're going to figure out. So let's actually do that. So we can get some probabilities directly from this question. So let's actually do that. So let D be the event you have the disease. Okay. Let say POS be the event you test positive. Let NEG, which is of course POS complement, but writing POS complement is going to be weird. So I'm going to write NEG instead. is the event you test negative. Okay. So if I give you all that information, there are some things that we can say here. What is the probability that you have the disease? Well, we are told that 1 in 10,000 people have the disease, so that's going to be 1 in 10,000, which is going to be 0.1231, right? And so now, what else do we know? We know that it gives a false positive in 1% of cases. What a false positive is that you don't have the disease, but the test tells you that you do, right? So that's a false positive. The test returns positive, but it's actually false. It shouldn't be positive. It should be negative. So what else we're told about is the probability that given that you tested gives a false positive in 1% of cases, which means, so this is given that you don't have the disease, that you test positive, right? So you walk into the clinic, you actually don't have the disease, but the test gives you a positive result. And now that is going to be 1%. Okay. So now, did I write 4 zeros here? I think that should be 3 zeros. What else do we know? There's a 99% chance that if you have the disease, the test will actually be correct. So we also know that probability that if you have the disease, the chances that you will test positive is 99%. Okay. Now, what we want is the probability that you tested positive on this test. What is the probability that you actually have the disease given that you tested positive? That is really, what is the probability that you have the disease given you had a positive test result, right? So that's what we actually want here. Okay? So that's that. Now there are tons of ways we can do this, but I'm just going to use Bayes' formula to do it. And we will see. So by Bayes, the probability that you have the disease given that you tested positive, that is going to be, remember, it's the probability, the opposite order, positive given that you have the disease times probability of the disease over probability that you test positive given that you have the disease times probability of having the disease plus, come on, iPad, plus the probability that you tested positive given that you don't have the disease times the probability that you don't have the disease. Okay, so that's Bayes' theorem. So that's this guy that we had over here. Right? Okay, so that is what we're going to do. Now we'll see what we have here. We know that P of D is this. Of course, that means that probability of D complement is 1 minus that. And so we can now go and we can plug this in if we have everything. Do we have everything? Yes. We have that. We're positive given that you have the disease. We have probability of the disease. Yeah, so now we could just go in and plug these guys in. Probably that you're positive, that's 99%. Probably of having the disease is 0.001. 3 zeros and a 1 over 0.99 times 0.0001 plus positive given that you don't have a disease is 1%. Times probability of not having the disease is 0.99999999. Okay, and I actually worked this out in the interest of time. I did the work for you, plugged it into the calculator. At least I thought I did. I guess I didn't. Let's actually do it then. I could have sworn I did. So yeah, let's do this. So 0.99 times, and you guys can check me on the answer here. Over 0.99 times plus 0.01 . Okay, and let me, what did you guys get? Are you guys trying it? Well, I'll tell you what I got. I got 0.0098.
Professor, how do you plug it into your calculator? Because I got 0.01, so I feel like I plugged it in wrong.
0.01. That would be correct if your calculator rounded it. So what this is 0.98%, which, I mean, your calculator might round that to 1%. So it's a matter of like setting your calculator to have significant figures.
Okay.
Yeah, which I don't know. Your calculator would have to, I don't know what calculator you have. Yeah. So the thing is, if you did any intermediate rounding, you won't get exactly the same thing. So if you did this separately and then did this separately and this separately, and then you cut off some decimal points and then plug them in again, you're not going to get it exactly. Like I plugged this all in at once. Otherwise, if you round in the intermediate steps, it might round your final answer. But yeah, the surprisingly, there's less than a 1% chance that you actually have the disease, which is a big difference from 99%. A lot of people would be like freaking out, oh my God, 99%. And I mentioned before that there are times when your intuition might lie to you, but now you can actually see a calculation where that actually works. So you might say, well, if you have the disease, there's a 99% chance it'll pick it up. And they're like, whoa, I got it told me positive. There's a 99% chance that I have the disease. No, there's actually less than a 1% chance that you have the disease. Right, so let's actually move on to the next one. So this was part A here. let's actually move on to part B. So you test positive for this disease, you swear you have it. You're freaking out, but your friends are trying to calm you. Just calm down. Why don't you get a second opinion, right? You always have that friend, right, that tells you to get a second opinion. So you do just that, right? Suppose you go get tested a second time by an independent lab, independent doctor. The two have nothing to do with each other. So you have independence, right? You go and you get tested again and you get positive results again, right? So now, man, it's like the universe is working against you. You can't catch a break. For sure now, the probability I have the disease is close to 99%. There's like no way that I'm not going to die in a very short period of time, right? That's what you're freaking out. So now the question is, what are the chances that you have the disease, right? So let's go. So now, several ways you can do this. But one of the easiest ways is to just update. And there's a secondary reason why I actually want to do it this way. Update that probability. Right. So now, before you walked into this doctor's office, right, the probability of you having that disease was 1 in 10,000, right? Now, what you're going to do is you now have a probability that's specific to you, right? It's not about the general population. This is the chance that you have the disease, right? So you can actually do this as the new probability of having the disease. So it's not actually 1 out of 10,000. Now, because you have a positive result, it's a little bit higher. It's at like 98 out of 10,000, right? So what you can do is you can use that as your new probability. So set probability that you have the disease based on a prior test that you did is going to be 0.0098, right? Of course, that means the probability that you don't have the disease is 1 minus 0.0098, right? So that's going to be 0.9902. Okay. Now, the other probabilities are going to stay the same, right? Because they have to do with the test, right? So the test will give you a false positive. In this case, it will actually give you a correct positive in that case, right? So still using probability of a false positive is 1%, and the probability of a correct positive is 99%. It's 99% effective when identifying that you have the disease. So now, the probability that you have the disease, given that you test positive a second time, is going to be, again, by Bayes' rule, chance that probability you test positive, given that you have the disease, or probability of having the disease, over probability that you test positive, given that you have the disease, times the probability of having the disease, plus the probability that you test positive, given that you don't have the disease, times the probability that you don't have the disease. And now these probabilities are slightly different. This one is still going to be 0.01. This is going to change to 0.0098. going to be 0.01 times 0.0098 plus 0.99 times 0.09902. Okay. All right, let's actually do that. So this is going to be, instead of the 1 in 10,000, that's going to, sorry, that was 99, wasn't it? Yes. I think I switched these. 0.99 here, 0.99 here, and 0.01 here. Okay, so we have 0.0098, 0.0098, and then 1 minus 0.0098. So is there a 99% chance? Now the probability, it does jump up, but it actually doesn't jump up to 99. You now have a 49% chance of having the disease. Which is still a far ways off from 99%, right? And that's the actual chances, right? Now, this isn't really something that a lot of people would find intuitive, but that's the actual answer. And the reason is because of the condition. What happens is that you actually change the sample space by taking the test, right? And so let's actually talk about, let me actually kind of show you why this works. The above may be surprising. Does it actually make sense? Because from your point of view, the test should be 99% accurate. There's no way that that you test positive and you're like you have less than a 1% chance to actually have the disease. Where is that coming from? So here's where it's coming from. So let's say this is the population, right? And let's say there are so let's say this is 10,000 people right here. Okay, so this is 10,000. Now we are told the probability that of having the disease is 1 in 10,000. So there's actually only one person on average in the 10,000 people who's going to have the disease. Let's identify that person. Let's put him right here. Okay. All right, so we have that. Now, what do we know about the test? The test is going to give you a false positive in 1% of the cases. Now, what is 1% of 10,000? So let me put these people over here. And make this people who get false positive. Right? How many of those people are there? So it's 1% of 10,000, which is like 100, right? Okay. So this is 100 people, right? So these are the people who would get a positive result. So, you would have about, 101 people getting a positive result. Right? Chances are the guy who actually has the disease, the test will say yes, right? There's a 99% chance. So let's just count him. Now, in addition to this guy who gets a positive result, on average, 1% of the population will also get a positive result, even if they don't have the disease. This accounts for 100 people. So really, out of 10,000 people, about 101 people would actually get a positive result. So now, when you say given that you got a positive result, this means you are 1 out of 101 people, right? You are now not in the general population. You are in the population that has gotten a positive result. So the result happens, right? Now, what that means is we saw that before. Once you know something happened, it automatically will restrict your sample space. All of these people don't matter anymore. You are now either the red guy or the guys in the green box, right? You are not someone who gets a negative result, which would account for the vast majority of the population, right? So now, when you look at that, like, oh, so probability, you have the disease. Well, that's going to be roughly 1 out of 101, right? And if you look at like 1 out of 101, should be pretty close to what we got before. Yeah, that's roughly 0.0099, right? And look at that. Bayes theorem tells 0.0098. Now, of course, why this is off is it's because we don't know for sure that the guy who actually has the disease will get the positive result. There's a 1% chance it's going to be slightly off. So you might be somewhere between 1% and 0.99% or something like that. You'll be a little off, just depending on how many people actually get tested. But now you'll see that if you actually think about the problem, not using your intuition, but actually writing down a diagram, logically thinking through it, you'll realize that this result actually makes a lot of sense, which in the beginning, it probably didn't feel like it. This is people who fall into this, which is virtually all human beings. People who fall into this, we say that they fall into the Bayesian trap. So it's like when a probability, your intuition leads you astray, chances are you're making a mistake with Bayes' rule. There was some condition that you didn't really take into account. You didn't really think it through and realize that, oh, this happens means that I'm a part of a different sample space, right? There is also a book called Thinking Fast and Slow, which it's a nice book. I'd recommend it. As well as a couple YouTube videos that I watched that really like talk about this nicely. I'll put this in the video description when I post it. But another example is something like, all right, you're walking on a campus, right? And you randomly meet someone and they're a very shy person, so you had to guess, right? Someone comes to you and say, all right, you just met a shy person, right? If you had to guess, if they were a business major or a math major, what would you guess? And turns out that most people would guess math major. So let's actually do that. Another example. It's a very fuzzy example. I'm just going to make up some numbers. You meet a shy person on campus. You are forced to guess if they are a math major or business major. Okay. Now you guys are pretty shy, but generally business students aren't. So most people would sort of say, well, you know, business majors, business is all about networking and building relationships, and you know, you have to talk to clients and stuff like that. Business people, you won't really survive in business very long if you're really afraid of reaching out to people. So yeah, I feel like the math person is the guy who would be shy, right? The math people are the people who just are there all to themselves. They're working, you know, they're sitting in a basement working on math problems. They hardly see anyone, you know. A math person is a guy, you meet him, he's staring at his shoe. If he's a particularly outgoing math person, he'll be staring at your shoes. Everyone knows that. Okay, so a lot of people would actually guess that, oh, it's probably a math major. Many would guess this, and chances are they'd be wrong. Now, why would that be wrong? Because you do have an intuition about, you have a prior intuition about who's shy versus who's not based on a major, right? So any major where you have to always be talkative and talking, like you'll probably guess that, oh, people in this major wouldn't be shy. But again, you're not realizing what's going on in the sample space. Bayes' theorem would actually tell you a different story. The thing is, why this is wrong, you know, likelihood is that there are way more business majors than math majors, right? In general, right? Well, probably it would be nicer to use psychology, but I wanted to use like almost everyone majors in psychology, right? It's like the most popular major ever. But even when you look at business, you'd have a lot more business majors than math majors. And knowing the proportion in the population is going to be very important. So a lot of people are looking at the entire thing when they really should be looking at the guy in the green box and the red box. So what would happen is, say, for every 10 math majors, and I'm making up these numbers, making up numbers. Let's not do making up, that's made up numbers. But they're probably close to the real thing. Say for every 10 math majors, there are 100 business majors. And let's say, even if we assume most math majors are shy, let's say 90% of math majors are shy. And say only like 20% of business majors are shy, right? So let's say even if we say your intuition is correct, and then yeah, chances are if you're a math major, there's a 90% chance you're gonna be shy. versus a 10% chance you'd be shy as a business major. What you'd realize is that here, 90% counts for 9 shy people, while 20% accounts for 20 shy business majors. Right. So the thing is, even though there's a small proportion of business majors that are shy, there's so much more business majors than math majors that even the small proportion of the business majors is a larger number of people than the majority of math majors. So this means there are about 29 shy people, and 20 of them are business majors. So, I mean, probability that it's a business major, given that they're shy, is actually going to be 20 out of 29, right? Which is very close to 2/3. Whereas the probability that they're a math major, given that they're shy, that you met a shy person, that's around 9 out of 29, which is roughly 1/3. You're actually twice as likely with these makey up numbers to meet a shy business major than you are to meet a shy math major, right? And this is the kind of thinking that Bayes' rule would save you from. This is kind of thinking that being very good at probability will save you from. You realize that there are a lot of things that our prior intuition of how the world works causes us to make like these very erroneous assumptions in terms of how likely something is, in terms of the proportion of things that would behave a certain way. And yeah, it gets you in trouble a lot of the time. And it can be downright wrong a lot of the time, right? And so Bayes' theorem is one of those things that it kind of saves you from your biases. You can, and as you'll realize here, you'll notice that I used Bayes' theorem once, then I had an updated probability and I used it again. And now I actually jumped. The probability changes. You realize that if I use it again, I would get even closer to 99%. If I use it again, I'll get closer to 99%. So what you can do with Bayes' theorem, it's often used iteratively. You use it over and over. So you start out with a guess for what you think the probability is, but you just know that you might be wrong. Your intuition might be totally off. And so what you can do is you can use Bayes' theorem to actually churn out a few of these things to kind of see what the real probability might be. So you'll realize you might underestimate or overestimate, and Bayes' theorem is actually going to tell you which one you did. So that's pretty cool. Yeah, so that's Bayes' theorem. This is a very common type of example. The 2 examples I gave you were pretty common. And I think in that book, there was also a very similar example, except they use like farmers and librarians or something, but I don't know if you guys would know about those. All right. Let's get through one of these. I want you guys to actually try the rest for next time, but I think let's do problem 3 first, since it will also use Bayes' theorem, whereas the other ones probably, yeah, no. I don't think any of the other ones use Bayes' theorem, but that one, problem 3 would. So let's actually use problem 3. It's a little bigger. On a table, there are 5 coins, but 2 of them are double-headed. you pick a coin at random and you flip it. What is the probability that the coin will show heads? So it turns out that you can actually do this based on Bayes' theorem. So version 1 of Bayes' theorem. So here's what we can do. So we have 5 coins. 3 are fair and 2 are unfair. We want the probability of getting heads. We know the probability of getting heads, given that you chose a fair coin, let's call that F here and U here, and is going to be 1/2. Yeah, that's going to throw on there. Fair, unfair. So the probability that, given that you chose a fair coin, the probability of getting heads, we know that's 1/2. Given that you chose an unfair coin, the probability that you get heads is actually 1 because it's a double-headed coin. So now you want to know what is the probability that you will actually get heads. So you want the probability of getting heads. Now, how would we do that? Well, you can use Bayes' theorem version 1. We know that the probability of heads is going to be the probability of heads given that you chose the fair coin times the probability of a fair coin plus the probability that you got heads given that you chose an unfair coin times the probability that you chose an unfair coin. Okay, and that's by Bayes' theorem version 1. That's this guy. So now you can go and you can put these guys in. What is the probability that if you have a fair coin, you get heads? Well, that's 1/2. What's the probability that you picked a fair coin? Well, there are 5 coins and 3 of them are fair. So that's 3 out of 5. Probability that you get heads with an unfair coin? Well, it's 1. What's the probability that you'll pick an unfair coin? Well, there are 2 unfair coins out of 5. So you have that. So this becomes 3 out of 10 plus 2 out of 5. So there's a 7 out of 10 chance. I mean, there are other ways to do this, and I might talk about that next time, but that's one way to do it with Bayes' theorem. This process is called, what we just did is called finding probabilities by conditioning. Right? So you find a probability, but you base it on a condition that you're in one group or the other group, right? So I know there are 2 different types of coins on this table. So what is the probability that I get heads if I chose a fair coin versus an unfair coin? So you condition on the fair versus unfair. And by doing that, you can apply Bayes' rule version 1, and that will actually give you the correct answer. Now, you could also enumerate. You could realize that if you have 5 coins, with 2 of them are double-headed, that will give you 7 heads total. And out of 10 sides, right? Because you'd have heads, heads, heads on the fair ones, tails, tails, tails. And then for the 2 other ones, you'll have heads, 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 right? So there are 10 sides because there are 5 coins with 2 sides each. And then if you count the number of heads, 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 you get 7, right? So you can count it numerically like that. But yeah, 7 out of 10 is going to be your answer. So we will stop there. We'll get through a lot of these next time. They use principles of probability that I already taught you, but we're going to do them. Problem 7 is going to lead us into another formula that I'll give you guys. And yeah, we will stop there. Okay, so remember the announcements. They'll be posted in the notes, obviously. But that's it. Hopefully you guys have a good rest of your Wednesday, and I will see you guys in the next one. Ciao.